Okay, so let's continue. So from last lecture, we have seen like the way to parameterize basically a deformation of a pair like Calabi-Yau and the volume form is given by this equation, and we see like this modular space is embedded into this somehow in the Calabi-Yau 3 example, like embedded into this H3 as a Lagrangian submanifold, from which we can rid of the pre-potential by a choice of splitting or of the Hodge filtration. So we're going to do this one in a general setting by incorporating this volume form, this moduli space of volume pair, so-called this kind of extended moduli space. And this is also this point of view by Barnikov-Kontsevich in their discussion of this construction of this Fabrice manifold associated to this data. So again, so let's rewrite this equation a little bit. So let's introduce a parameter. A formal parameter. And this variable has degree 2. This parameter will play the role of like gravitational descendant in the B model. Now, and introduce the combined differential Q. Now, we can write this equation, these two equations. Now, in a simple equation as follows, like mu Q applied to mu tilde plus 1/2 mu tilde equals 0. So his mu tilde, if you take this combination, it's like mu plus T rho. This is one of the key observations. So if you send t goes to 0, you recover this deformation of the complex structure. In the linear term in t, you get this equation, and there's no higher term in t in this equation by this choice. This is like a mu is like a poly 1 1. Rho is a function, so it's a poly 0 0. Okay. Now this motivates the following extension to incorporate such deformation problem as follows. So we introduced a new DGLA or some kind of shifted version, but I won't distinguish like with like this shifted or not this shifted. But this data, like polyvector field, with one more variable t added, formal variable t, and with this differential q, this operation, and the same bracket as before, which is extended t linearly. Okay. And so now, somehow this complex capture the deformation of Calabi-Yau geometry in a way. So, bunch of remark. This data can be viewed as a homological replacement of the like volume preserving vector field. So And what is a volume preserving vector field? It's given by divergence free vector field on my Calabi-Yau, so kernel del. With this differential given by d bar. So you can write in such a way. So you can write this divergence free vector field in terms of this complex. So here it's like a poly T del, and you got T here and T del, T square PV, and etc. So this is the original place you play with like divergence-free vector field. That's basically the symmetry of the Calabi-Yau. Now you replay this one. This is badly behaved by this guy. This is somehow much better behaved. I will show you about this fact, and which is captured by this complex. The first thing I want to mention second, did I mention this one? Let me write it here. Like, T is basically the bimodal version of gravitational descendant. And third one I want to say, like the original like DJOA, like polyvector field, del bar, and this bracket. You see, like this theta give rise to extended deformation of the extended moduli space of X. And now the way you basically incorporate the additional data from the volume form, this additional direction leads to this equivariant version. And you can somehow view this one as extended moduli of the pair of Calabi-Yau geometry. Okay, that's one thing I want to say.
So what's the difference between looking at is a DGLA or as a family of DGLA parameters?
How can I say? You can view this one as a family. It's like a what is a good way of saying it? Actually, you're absolutely right. This bracket is actually is linear in T as well. Yes. Maybe you don't see this distinguishment like at this moment, but this T has a particular meaning as a gravitational descendant. That plays a role. And because you see later you will see, like when we discuss the sympile structure, this T also will enter into this higher residual pairing, things like that. So that's really happens for every point on the moduli. Then when you vary the moduli, the whole data varies. That's more natural to view this one as the data of the series, not the moduli. But you can say, like, okay, well, let me just view this Calabi-Yau volume form rescaling as a parameter. That's also okay. And this is like an equivariant parameter. So you think about this operation as saying that, okay, well, this is looks like a operator whose kernel, the fixed point of this. Think about this one as a vector field. And the fixed point of the vector field are given by divergence-free vector field. So you want to pick up the fixed point, and this is why it's like suppose this one arises from some x1 action, and this is the fixed point of the action. Then this is basically equivariant fixed point. So that's part of the data. And I will not view this S1 action as a parameter, but Yeah, but formally as algebraic data, you can do that. Yeah.
So rotation around.
It's actually a rotation on the worksheet. So the reason you have this data, probably let me write in such a way. So later when we discuss the worksheet B model, it's really given by some kind of some sphere, or some kind of a Riemann surface to target, shift it. And if you look at local observables, and because the theory is topological, local observables is given by function on the target. That's the first one. But if you look at equivalent local observables, you'll find the second one. So the real data of this guy is given by equivalent local observables in the worksheet B model. That's the better explanation of this how this one arises. This also explains why this is about this gravitational descendant is line bundle on the modular space.
Well, because I remember gravitational descendant, is there a Virasoro conjecture on this side?
There's a Virasoro thing. Actually, probably we'll discuss this Virasoro structure today or next time. Yeah, this can help us to do the calculations, to write down explicitly the generic function. Yeah, because it's going to be the geometry of the symplectic space arising from this data. So, and that's how actually Giventel interpreted his Lagrange cone having this Virasoro symmetry. I'll talk about it later. Actually, without that Virasoro symmetry, it's difficult to figure out the formula for the BCOE action. I will explain this. So here's one of the things I want to really point out. This is a big puzzle for me for a long time. It's the following. So let me start with the question. Can we actually express this kind of equations as the variation critical point of some action functional? You see, when we study classical physics, usually it's controlled by some action functional. And if you study the critical locus, you do variation, you find the equation motion, and that's about the classical physics. Then, with the help of this action functional, you can quantize this. Okay. You can quantize the theory using path integrals and things like that. And it's very puzzling here. Again, you have this Calabi-Yau geometry and Calabi-Yau volume form and compact structures. And this equation is the equation describing the B model closed string field. And then you may ask whether this is an equation motion for something. It turns out to be highly non-trivial. So the original work of BCOE that says the following, on Calabi-Yau's threefold. And if we work with the symmetry of the Calabi-Yau structure, divergence free vector field. Well, divergence free Pauli vectors. So you work with basically element in this kernel del.
So what's the analog in the A side equation?
Which equation? These equations. Oh, I don't know. In modular space of a Kähler structure. Yeah. Modular space of Kähler structure. Yeah, it's very boring without No, the linear structure is boring, but the quantum geometry is non-trivial. Yeah.
Because you are not being quantum correct.
It's just like d omega equals 0. Yeah. But you have quantum corrections.
And all the quantum corrections.
Yes. Yeah. Exactly. Yeah.
So you basically have BB infinity structure, so you can also write the same. Similar.
Yeah, quantum correction.
Yeah, that's why you have to incorporate quantum correction. Yes. Yeah. Okay. Then, if you work with divergence-free polyvectors, then this equation. Describing the deformation of complex structures, indeed can be written as the critical point of some action function, which is called a Kodawa-Spencer action, and described by BCOA paper. This one is called a Kodawa-Spencer. Gravity action.
So all this is really used for a linear in particular solution.
Which solution?
Because you're fixing a gauge. The linear in particular cannot be free to look for the linear by cannot.
Yeah, but this action also has a gauge symmetry, so it's like Chen-Simons. This equation,
Yeah.
without the gauge fixing, it's a critical point, but they have to model this symmetry of the action.
Can you write without the choice of the fixed background complex structure?
Oh, background independent equation. That's not no. Yeah, that's one of the most somehow mysterious part. Like, suppose we want a background independent story, but this, you need this background to write down this equation. And one way out is to say, okay, well, we will have just different formulations and different backgrounds. They are connected by some kind of flat connection, just like what you do in this geometric quantization. And that's that's the role of this holomorphic anomaly equation, as Witten explained. You move around this modular space. It's like every modular space. When you quantize things, like you find Fock bundles on the modular space, then it carries some kind of projective flat connections. You move around. That connection literally is about holomorphic anomaly equation. So this anomaly equation will help you to identify different points. But you are right. I mean, there's if you want to just write down something which is completely independent of the background, this is a mystery. Okay. Now, one of the problem here is let me write it here. The problem about this approach. It's like this one violates some kind of a locality and some locality. This kind of data is violated by a bunch of reasons. For example, this guy, this element is not like a module over smooth functions. So you cannot localize things like by multiply by some kind of a bound function or things like that to localize some local observables. So this one is not, say, infinity module. This is one of the puzzle. The other one is like one of the term in the Kodawa-Spencer. It's also non-local. And this is more serious. Like, in a way, this is non-local, and you cannot do this kind of local observables, and it give rise to some obstructions for doing quantization and things like that. So now we're going to do something a little bit different. By enlarging this equation, not enlarging, but actually it's the full information coming from this Calabi-Yau geometry. So let's consider the Calabi-Yau geometry. And now our mu is an element of this polyvector field with all descendants turned on. Then you can write down this equation. and you ask the same question, like, okay, well, for this equation, can you write down some action functional whose critical point give rise to this guy? Yeah, unfortunately, I couldn't find one. I mean, I tried for many years. So this is like no action. It sounds like a familiar problem in physics, like you have some kind of a system where you cannot write down equation motions. However, there is a metric here happening. The metric is the following, like, although this equation cannot be written as the critical locus, however, you can perform an L infinity transformation and such that after you do this kind of nonlinear L infinity transformation, this equation becomes something like a more complicated version, like something like that. I will explain this in detail later. So, roughly speaking, here's what's happening. So if you do some kind of L infinity transformation, you will get a different Morikawa equation incorporating all this higher bracket. And for this one, now you can find an action. That's the metric. And we call this one BCV action. And this is the point of view in my work with Castello. I will explain this. And the one thing I want to mention is about the role of this L infinity transformation. This one is literally given by period map. So that's why I always try to like emphasize the role of the period map. The period map leads to a solution of the problem for writing down an action functional. Okay, so how this works?
So what's the difference between L1 and Q?
There's no L1. L1 equals Q. Yeah.
There's L1.
Yeah, that's L1. Yeah. So this here start from 2. Yeah.
Do you have something with L0?
No 0 here. Well, if you turn on Lambda Ginsburg, it's different story. Yeah. Okay. So let me show you how this works. It's again about period map and about this geometry of the Lagrangian submanifold. So let me show you how this works. So let us first define a couple of objects related to this construction. So to simplify notation, let me call this one Sx. Defined to be the following object: polyvector field with descendant. And actually,
this is where you. So over there, the view has no T, right? Over here, you have to have a T.
there's no T here, yeah.
But this one, you have to have a T.
Yeah, this T is important, yes. And so this place here is like, this one is Lorentz series. And I want to shift all degree by 2. So such that the usual deformation of the complex structure and the volume form sits in degree 0. So this means like mu plus, so this is like a mu plus T rho, the object here has degree 0. So if the standard, the classical moduli sits in the standard object, the degree here. Now, so this 2 means like the shifting by degree 2. It should actually, for this object, it should literally be better to work with this object after this shifting. And let's call this one S plus. by this non-negative orders, and that's the object where we write down the action functional. And let's call S minus the opposite part. And we are now in a very similar situation as what we have seen in this period map. This guy can be written as the sum, direct sum of these two. And then we'll see actually this is going to be a splitting by isotropic subspace. But I have to understand what is the corresponding symplectic structure.
But this is not on the form level, not on the logical level.
On the chain level, yes. Yes,
Okay.
on chain level, yes. So yeah, let me just write it. So this is really the Q axon here. So this guy is a subchain complex of the bigger one. However, this guy is not a subcomplex, so this Q doesn't preserve the splitting in a way, and this will play a very important role. So it is about this data which leads to the so-called classical mass equation. I will tell you about it. Okay. Now, so
Is this never, let's say you got Taurus or something?
never, yeah. This data because this is really about like Hodge filtration. This never holds like literally just as long as this operator. The issue is about this operator. You apply to the leading term here, it goes away. So this term, this is never preserved. Now I want to say that this is actually the same thing as like you can write this one as a splitting by isotropic subspace, and then what's the corresponding symplectic parent is the following. Like we define the so-called T sesquilinear pairing. On the space as follows, and this is actually this pairing. The original place I saw this pairing arrives from the work of Kyuji Saito in his higher residue theory. I will actually come back to that point later when we discuss the Landau-Ginzburg twisting. But the formula is the following: like suppose I have. So let me first write down where this one is. So it's a pairing on this space. It's going to be a symplectic pairing as follows. So omega ft is a T here
On the left,
on the left.
right hand side. Right hand side.
No T. Oh, yeah. I already take the residue. So before you take the residue, that's higher residue parent. So this omega is the residue of the higher residue parent. I gotta distinguish these notations. Like this is gonna be called omega. The higher residue parent is gonna be called K, and I'm gonna write K later because so far we only need this omega. But later we will discuss the geometry of the Frobenius manifold. Arising from this data, we're going to use the K. Yeah. This definition is given by, so alpha beta give a polyvector field, so you can pair them using the trace pairing. This depends on choice, depend on the Calabi-Yau volume form. Then on the t parameter, you take this and take the residue to be 0. Okay. Now, so this is my definition of the parent. Now we're gonna see the property of this parent. First one, this is like a school symmetric. It's really like symplectic parent. So observe. So if you really calculate object here, like say if you switch the order, like what you do in symplectic geometry, if you switch the order, and by definition, it's given by trace beta alpha and the residue like gt f minus t dt. Then if you switch the order of the trace, like this is gradient symmetric, and if you switch of these two, you get a minus sign. So it's a minus alpha beta trace alpha beta and residue ft g minus t dt. Because here you only pick up the order like -1. So when you switch the signs, you will get a total minus sign here. And this is given by minus the degree of alpha beta omega ft alpha gt beta. So you see, like this is a gradient school symmetric.
Can I ask why multiply residue pairing?
Why for
For example, if f and g is constant,
it's 0? Yes.
so
Yeah.
why want to define like this?
So these two are like opposite. So you want to write this one as like a quotation bundle. So this is like positive part and negative part. They're a pair. They're dual of each other. Yeah.
But one of them is finite dimension.
This is infinite dimensional space. This is a symplectic parent. This is a symplectic parent on infinite dimensional space.
But the S plus and S minus is one of them.
Both are infinite dimensional. This is an infinite dimensional.
The infinite dimension both ways.
Yeah.
Infinite dimension, because you look at all four of X, the probability of X.
And on T.
Infinite dimension is dependent on T.
Yes. Yes.
This is symplectic function about T and power.
Like what is the meaning if I just try to do the same thing for any S1 equivalent for more review?
That's why. Yeah. This basically the. It's really. You're right. It's really about the parent on the. It's a parent from this guy with this guy, and to get us this guy, and the trace on the partition function on the sphere. Yeah. It's just this parent. Yeah. And they have to reverse the orientation. So in a way, so it's a sesquilinear. You know, it's somehow. I think this is like what, for example, in the A model, people do this symplectic field theory. They use this parent. I believe so. So now, and if you calculate the degree, so it's not only non-trivial, like only non-trivial. You see, like the parent here, like for this one to be non-trivial, alpha batch beta has to be like top polyvector fields. So the degree, you can compute the total degree. So degree alpha batch beta plus degree f plus degree T. Now, if you calculate the degree for the polyvector field, this has to be poly dd in order to be non-trivial. So this one has degree 2d, and the sum of these two has to be t to the minus 1, and t has degree 2, so this one has degree 2. So this is only non-trivial when the insertion, if you view this one as a polyvector field, computes degree, and the other one is 2d minus 2. But remember, we shift the whole thing by degree 2. So by this calculation, you find the following. So here's the statement. If you also take into account the additional shift by 2, you see like this space is d minus 2d, 6 minus 2d shifted symplectic. In particular, on the Calabi-Yau threefold case, this is literally the symplectic parent. Otherwise, this symplectic parent has a degree.
In the dimension 6 case, the Calabi-Yau threefold case,
Yeah.
how does this symplectic vector space compare with the H3?
Yeah, I would say that. Yeah. That's actually this is the reason that if you apply this machinery and restrict to, you want to, I can say no. I mean, but maybe. Okay, just for your question, like the way it works is as follows. Like on Calabi-Yau threefold. And actually, this is the reason why a lot of people try to write down the normal equation for other dimensions and get it wrong. The reason is the following. Like for Calabi-Yau threefold, we have the splitting I will explain to you later, pretty soon, that the role of the period map allows you to identify this polyvector field with the cohomology. in this case, it's given by T poly 0, 0, poly 1, 1, poly T minus poly 2, 2, and T minus 2 poly 3, 3. That's how these two objects are identified.
No, identify this form, those are the space.
By contracting with volume form.
I think it's get map, no?
Yeah, cohomology. Yeah. So this. Yeah, let's call this one cohomology. Yeah. Yeah. Let's write this one as an omega. Either one. Yeah. You can see that there's a natural identification between polyvector fields and differential forms, which works for all Calabi-Yau and respect Hodge filtration. And if you apply that construction in this setup, you'll find this four components identified by this guy. So you see, like this is exactly the higher parent. Now this is a symplectic parent here. By pairing these two objects, that's the parent of these two, and pairing these two objects, that's the parent of these two. I'll show you this map later. I call this one gamma map. And this is not true for Calabi-Yau of any other dimension, only for Calabi-Yau 3. If you apply this one to any other dimension, you get a wrong degree of the descendant. So whatever you calculate is not literally the same as what B model is calculating, but only true for Calabi-Yau threefold. So where we are, okay. Now, another thing I want to mention, the proposition here. Let me write it here. I'm gonna let this.
It's not true because they're very similar. You need a complete comment or
Yeah, if you try to do the same thing, say for Calabi-Yau one-fold or Calabi-Yau four-fold, and you will find that if you identify with polyvector field, the data from the B model, that the corresponding component, the T component, the sum of these two is not 1 anymore, not minus 1.
then you define as the parent.
That is not compatible with the Hodge structure. Yeah. You will see. I will discuss this point later. Yeah, this is actually a very important point. Otherwise, I want to say like Q is graded skew symmetric. With respect to this omega. So I think I'm gonna leave this one as an exercise. In this exercise, you will see the different roles of d bar and the d. So basically, you show this operator is skew symmetric. This operator is symmetric. And under this sesquilinear pairing, if you combine this one to be Q, and then the whole thing is a symmetric. Yeah. This implies descent to cohomology, yes. Now, once we have this object, now we can understand pairing map. We're going to first do this one at the, we can do this one at either the cochain level or the cohomology level. Both are important. So now we consider first the cochain level or chain level pairing map. And actually, I'm going to call this one, let me just call this one pairing map. And the map is the following, like, this is a map which allows us to write down action function later. So S plus map to Sx. So first let me write down the formula and explain what it means. First of all, this is defined as a map of formal manifold, actually as a functor on Artin rings. So what this means is the following: like, it looks like this guy have a problem, right? If you do power series expansion, this is no longer Lorentz series. But as far as like a moduli space, local moduli or on the formal moduli space is concerned, this is okay, because just remark, this P is understood as a functor on the formal scheme of a map on formal scheme. This means the following: like, it's a modular functor, so you apply, this is fibered over any kind of Artin rings. So for any kind of Artin ring, Artinian ring, it's like a deformation problem. It's the maximal ideal in this Artinian ring. And this map really is like, if you evaluate this functor on this Artinian ring, and literally, this is the map, valued in this maximal ideal map to and because it's Artinian ring, if you do Taylor series expression for this one, it truncates at final order. So this is it pass to this formal scheme.
So T goes to 0, what makes sense?
T goes to 0, not make sense in here, but it makes sense here.
Yeah, because 1 over T.
Yeah, this doesn't make sense. Yeah, that's right. Yeah. And that's why you have to view this one as like a formal neighborhood of something. And to connect with the, you see, like, this is somehow, I write this shift here. This shift is about so-called Dilaton shift. And yeah, let's try to say a few more about it. So this one is really a short remark, but if you really want to understand this one like rigorously, and that's going to be the way you do it. But I won't say more about it. Like, if you really want to figure out the precise meaning, I mean, you have to work with Artinian rings. But literally, the formula looks like this. Now, let's draw the picture about this map. So this is my Sx, and this is my S plus. A mu here, a map by this period map. And now I'm gonna write down something very similar to what we have seen in the previous talk. So it's like a formal neighborhood. It's around it's basically around this origin. Let's first compute. For example, the tangent map. You see, like this map, like when mu is very small, because E minus blah blah blah. You see, like this is like also centered at the origin. So if you compute the tangent map, so you map this like a very first order map to. If you only look at first order, it becomes like T E minus delta mu over T. Expand in first order is like a minus delta mu. So you see, like at the first order is literally is a map of this xx to the same thing, but with a minus sign. So let me write this map as like the tangent map dp at the origin. So and we get identify this tangent plane by this Sx, identify this one by S plus x. And this map is really embedding by sending, it's like standard embedding with a minus sign.
Picture the draw is not.
It should,
Those should be flat, right?
no,
This
it's
is S plus S minus.
S plus, this is S plus.
Yeah. So the tangent space you send S plus to S plus. And the tangent to that origin.
Yeah, so probably I should, yeah, what is this?
Yeah.
Yeah, you can draw much better pictures, but okay. Probably you should draw it this way. Yeah. But anyway, this is like ransom manifold. I'll tell you that. But anyway, yeah, you're right. You're much better artist. Yeah. Yeah. Okay, but this is a precise statement. Yeah. I probably draw it wrong. Yeah, you yeah. Okay, so let me just draw it. Look. You more happy about it? More happy? Yeah. Okay. So because tangent map is actually embedding, you see, like as a formal manifold, this is really a formal embedding locally. So this implies that it's a formal embedding. So embed this space into our bigger space. So this is like, but this is a nonlinear object. So it's embedded as a nonlinear manifold. Point 1, point 2. The second point is also very important. This map is actually a L infinity transformation. Between two objects. That's the most crucial thing. The left-hand side, this space.
So when you say it's period map, that means to satisfy the more than 100
This is the one. Yeah. This is another way to say the second point. Yeah. So on the left-hand side, you have you have a differential and a bracket. You have a DJLA. You have the Mori-Cardano equation, so on. So this is given by Q and the bracket. And this period map, it can be this one as like a L infinity structure, DGLA on the space. Now, on the right hand side, this guy, we can write down a very simple, like a DGOA by just saying the differential is Q, and the bracket is 0. That's why it's related to the period map. And then I claim this period map is a morphism intertraining this DGOA with that DGOA. It's a map of L infinity morphism. It's really a L infinity morphism intertraining these two DGOA, but it's highly nonlinear. So why this holds? You can compute it, but the easiest way to see this is the following. So you know, whenever you have an L infinity morphism, you will map the Maury-Cardan equation on the left hand side to the Maury-Cardan equation on the right hand side. This is literally what is happening. So for example, let's just check this. If you see the image of the period map, like T 1 minus e to the mu of t, this is highly nonlinear. But after you look at the image, you look at the corresponding vector field here for the DGOA, you only apply Q. So what this one is, Q is like d bar plus d del, and from the exercise last time, you will see this equals minus Q mu plus 1/2 bracket mu e to the mu over t. So you'll see the original point satisfy the Maury-Cardan equation if and only if the image of the point satisfy the Maury-Cardan equation on the right hand side. So this precisely says this is a L infinity morphism. So this implies that Q mu equals 0 on the left hand side is the equivalent to Q, the period map applied to mu equals 0 on the right hand side. This is another way of saying this is an L infinity morphism.
Why is this infinity is DGOA morphism?
It's not DGOA because it's nonlinear. You see, DGOA is it's you have a Lie algebra, G1, G2. DGOA means you have a map, linear map, respect differential and bracket. But this is nonlinear map.
What's a nonlinear map holding one DGOA to another DGOA?
Yeah, the nonlinear map is about L infinity morphism. Yeah, it's not a map of DGOA. Yeah.
What's a nonlinear map holding
Yeah, it's a L infinity morphism between two DGOA. Let me say it this way. Yeah. Okay, so, and if you try to understand what this one says, so this implies the following, if we view Q as a vector field, important vector field on Sx, and so
This is a very general statement, right? You're not using any specific.
No, it's very general statement. Yeah. You're right. That's why I can generalize all this kind of thing even to categorical setting. Yeah. This is basically what Nick Sheridan was doing. But let's focus on this geometric side. You will see all the most important aspect from this, just on this Calabi-Yau geometry. So you see, this one says the following: this vector field Q is a push forward of the vector field on the left hand side, describing this L infinity structure. So another way of saying this is the following. So then Q is tangent to this guy. So let me draw the picture here. It's my S, X, and let me draw in this way. Yeah, I'm more happy about this drawing. Then this one says the following: I view this Q as a vector field on S, and then this tangent to this Lagrangian submanifold. Yeah, that's the consequence of this fact. And
We come to the way you draw. The Q is always horizontal. The image is curved, and it's always curved.
the Q is just linear, it's the same. This Q is the operator.
Yeah, no, but the picture you're drawing is tangent only at the maximum point.
Yeah, it's a formal neighborhood up here. So yeah, draw it a little bit. I think about this one as a formal neighborhood of the point.
But still, the other is going up.
But this is one vector field. But this tangent plane is infinite dimensional.
Yeah, no, but the vector field will not be horizontal. Right?
No. I probably it's better to draw this one. Yeah. Probably it's better. You're right. Probably it's very confusing. So let me draw in this way. Yeah. You are really geometry. Yeah. Yes. Okay. Yeah. And the way to understand this is the following: like, you have some kind of a vector field on the left-hand side, living here. That encodes the DGLA. And if you do the push forward, you obtain this vector field. Yeah. And that is precisely the vector field obtained by restricting the vector field Q to the Lagrangian submanifold. And I haven't been saying this is Lagrangian yet, but this, yeah. And we know from like classical mechanics, whenever you have some vector field, if this Hamiltonian is tangent to the Lagrangian submanifold, then you have a Hamilton-Jacobi equation. The next time I will show you like Hamilton-Jacobi equation is the same thing as so-called classical mass equation for whatever you got. But we're gonna do this next time. The third thing I want to mention is the following: like the geometry is like this guy. The image of the period map. It's really a formal Lagrangian submanifold. It's highly nonlinear, but it's a Lagrangian submanifold. Literally, it's 6 minus 2D is shifted. Yeah, it's a manifold. Yeah, I won't distinguish the convention about shifting. Just say it this way. And okay, so the way you see this is the following: like, if you want to show the tangent plane now at each point, basically, it's an isotropic subspace of this of the space. And so what is the tangent plane? So if you calculate the variation of this period map, you do the variation, and you find this is the same thing as like a minus delta mu. And this variation, because mu is an element from this S plus, so it's really an S plus x e to the mu over t. And now you observe that this actually is a Lagrangian is isotropic subspace of Sx, or let me say, let's write a lemma, a proposition. So for any element alpha beta in this S plus x, if you calculate the symplectic pairing, and it's going to be 0. So this is going to be exercise. Yeah. So in summary, we find the following: like, we basically explained that this geometry of this.
So you're arguing this is isotropic, right?
Yes.
So
yeah, it's infinite dimensional, so it's hard to say precisely.
Well, you have to say that the normal is cotangent.
Yeah, because at the origin, the tangent place is literally this one. So it's a little bit deformation of this guy. Yeah. So formally, it essentially can be identified with this one nearby, a little bit informal neighborhood. So essentially, it's a deformation of this guy in the isotropic subspace. So in this sense, you view this one as a Lagrangian. Yeah. So in the same sense, like this S plus, you view this one as a Lagrangian linear Lagrangian subspace of the big space. In the same sense, because actually the only thing we're going to use later is to use the fact that this guy is transversal to S minus in the small deformation.
Why is it so formal? Because mu is you get convergence of mu if you have the particular complex function.
No, it's not formal for mu. You can do analytic in mu if you look at the modular space. Yeah, that's no problem. Actually, you can also try to make the T analytic in a way, circles. I tried to write down something.
T cannot be zero. T has to be away from zero.
Yeah, if it's on a circle, I mean, really, yeah. But anyway, at this moment, if I really work with that like formal power series, and that's going to be the formal Lagrangian. So this formal is really the issue about this somehow the T. Yeah. Okay, so that's what we get. Like we find the period map as the image of which maps our moduli in a way at the cochain level into this space, which is purely topological in a way. You will see like this is pretty linear at the cochain level as a Lagrangian submanifold. And then you can do a bunch of things. Like first, you can write down the generating function. I'll tell you how to write it down.
Say again, Q depending on the choice of capital omega for the background. Omega,
Yes,
right?
yes, that's right. Yeah. And this picture is on the central fiber. But the modular space is embedded in the. It's like you have to use Gauss-Manningh connection to move around. So we have seen like the same picture as we have seen in this like Calabi-Yau threefold period map. Now we have a Lagrangian manifold. Although this is like infinite dimensional symplectic space, and later next time I will show you like you can write down the generating function of this Lagrangian. If you try to do it, you'll discover like intersection parent on the modular space of the, like pointed rational curves, the psi-class intersection. That's by exploring this geometry. Second, we will explore this geometry of the vector field. So you see like this vector field is tangent to this Lagrangian. So we know from classical symplectic geometry, we have this Hamilton-Jacobi equation. And this Hamilton-Jacobi equation, it turns out to be the same thing as the classical mass equation. So we're going to discuss this next time. I can probably stop here today.